Hi, this is Stephanie Kwame, and today we're going to talk about the science of structures and as they have to do with buildings, bridges, and roadways. This book was impressive to me. It's called The Structure of Scientific Revolution, and basically it starts out saying that we accept as facts theories based on what society thinks is true at the time. For instance, around the time of Christopher Columbus, they thought the world was flat, and now we know that's not true. But that's followed by a big interest in the theory, and basically it turns around to be revolutionary, and this is called revolutionary science or a new paradigm. This book actually came up with the phrase paradigm. One time that you would call that would be revolutionary science or a new paradigm was the Renaissance. It was a great revival. It's interesting how great people are born at that time as well. And so we had two geniuses born during that same time frame in Leonardo da Vinci and Michelangelo that helped that come about. Another one that was very significant was the Industrial Age. And then you look at people that were that lived at the same time: Albert Einstein, Nikola Tesla, Thomas Edison, Henry Ford, and there was others as well. And it was during this industrial age that structural engineering began, and we also relearned the reinvention of concrete happened. The Greeks had structural engineers, and they actually did their colosseums and stuff out of concrete. But we basically lost that, and it was reinvented around the industrial age. We learn from our mistakes, or we should learn from our mistakes. It's said in engineering especially, but I would say any field or every person has to learn from their mistakes, and if you don't, then you're bound to repeat them. And especially in structural engineering, when they make a mistake, it could cost lives. These are some examples of something that structural engineers could have made a difference in. And one would be the space shuttle Challenger disaster. It was on January 28, 1986. At that time, everybody was following NASA and very interested in the space program, and television sets would be turned to watch the Challenger lift off. And I know I was, and watching it descend into the sky and then blow up was just mind-blowing. It was horrific. And it was believed that the O-ring seal on the right solid rocket booster failed. And you know that O-ring, who was built by a company called Thiokol, had been inspected. They had used that type of O-ring before. They never found that there was a failure in the design or a flaw in the design. And you know, the government inspected it as well, and the failure was due to a faulty design. So they just missed that there was an issue with it. Another is a Chernobyl nuclear meltdown. This was in Russia, and it happened on April 26, 1986. The reactor there was a Russian-built reactor, but it blew up, and it released over 400 times the amount of radiation that the bombing of Hiroshima did. And human error played a little bit in it, but it was also had a problem with the control rods. So what happened is they were doing a test of it, and the operators weren't really trained well. And it was known that the control rods would fail on a low power test. And then when it failed, it would start to shut the reactor down. And as it started to shut down, the operator, because he was really trained to keep it up at all costs, to keep the electricity going, he tried to bypass the systems, and the result was it blew up. And now here, 28 years later, that city remains vacant. Nobody can live in it. It still has high radiation, and it's intolerable for people to live in. This one is studied when people become structural engineers. This was the worst disaster up until the time that we had 9/11. And it happened, it was two walkways that were in the lobby of a Hyatt Regency hotel. And the contractor asked for a design change. And the structural engineers allowed that design change without really looking at it, and they were found guilty of gross negligence. So on July 17th of 1981, the two walkways collapsed, and the lobby was filled with people doing a dance or having a dance. And they found out later that the two walkways weighed 64,000 pounds. And the late design change put more pressure, or the upper walkway, instead of having them both have equal support, the upper one had all of the support, and it didn't really, if you did the numbers, it couldn't even support itself, much less the other walkway, and it just collapsed. So they had insufficient load capacity. So structural engineering is usually considered a discipline within civil engineering, but they ensure that our buildings and our bridges are safe through all kinds of things. They also design structures to be stiff enough so they don't vibrate beyond acceptable limits. And a classic example of that happening is the Tacoma Narrows Bridge that beat itself to death. And there's also fatigue, so there's variations that they have to build into when they give a stamp and say, we can build this. Their job really is to prevent or reduce loss of life or injury. Below, on the bottom of this page, you can see some FEA examples, finite element analysis examples. And there's lots of programs that they can use to come up with examples. And so this actually shows the failure rate in colors. So the blue would be solid as a rock, and then it goes down in different colors, and red is that you've got trouble. So the suspension bridge is really secured at two ends, and that's stable at both ends, but as you get to the middle, well, over time it could get worse even. It's still safe. The abruptment for a freeway has red on it already, so that one is bound to fail. It needs to be redesigned. And if you ever drive into a parking garage, take a look at this one and know where the weak points might be in that parking garage so you don't park there. But anyway, they basically determine or analyze these structures. And talking to structural engineers, I have found that they want people to take responsibility for the calculations and to have some idea about what it would be, because when they crunch the numbers with computers or computer programs, if everything isn't in there correctly, the numbers could be way off, and they have to be able to know if those numbers are correct or not. And so we're going to do a simple task in structural engineering called the pavilion, and we're going to work the numbers to figure out if it's going to be safe. And to do that, we're going to use our program that we use, which is ArchiCAD, which is a building information modeling program. There is a tutorial on the instructor portal that goes step by step on this, and so after we finish this, then we can get busy on the project, which is the tutorial. But I'm going to give you a brief overlook. We're going to place in a slab. I'm going to give it a beginning point, and I'm going to use the tab key and put in 36, and it defaults to feet, and then tab again and put in 24, and then enter, and I've got my slab. Next, we're going to put some columns, and we're going to put in columns that are 1 foot by 1 foot, and they're going to be right now on each corner. When I see the check mark, I know that that is connected, and apparently these are measuring from the center point. So we're going to go in and quickly fix that, because we want those to be on the slab itself. So I'm selecting the arrow so I can edit. I'll take this grip and move it so you can see it's easy to move them. And now what we're going to do is put on a roof. They're 10 feet high, by the way. So I'm going to double click here and make that 10 feet. And the roof is going to be a gable roof. So arrow over till you see gable. And the way you put on a gable roof is you pick a point here and select a point here and then slide it up. And there we have it with some offsets, some default offsets. And this is what we did. This is our beginning of our pavilion. And we want to make it sure it's safe so that when people have picnics under there or they run under there for safety in the rain, that it's not going to fall on them. Let's go back to the first floor, and we have roof highlighted here. If I do Control A, it will find every roof, and there's only one. And we're going to go to Design, Roof Extras, Roof Maker, and the Wizard. Everybody likes a wizard. Now you can change the width of things, and you can change the way things are here. But we're going to leave it just as it is. But we are going to change the layer. It was on a roof, and we're going to change to a picked so that we have the roof and the beams on a different layer. We're going to say OK. And now the computer is calculating for us. And there we go. Let's take a look at that. And in order to see it, we are going to do a Control L for layer and take off the roof layer because we put that one on a picked and it's on so we can see the rafters in there. And now what we're going to do is we're going to calculate. Whoops, I zoomed in just a little bit too much there. But anyway, we're going to calculate the rafters, and this is what I meant to do. So the weight of the rafters, and you'd be surprised at how much that wood weighs, and then figure out the load that these columns can take and see if it would be safe to build, if the people underneath it could be safe. So that is the project for today. And I guess you could kind of see if you would like to go into civil engineering with this project as well. So have fun, enjoy doing it, and thank you for listening.